Hello, everybody. Um, Thank you for joining me today. We're going to be talking about building trust in generated AI code, specifically for semiconductor design, and talking about addressing some of the data provenance, data quality issues that are associated with generative AI technologies. Standard confidentiality statement. So one of the problems that we will discuss today about AI, specifically generative AI in the semiconductor space, or a series of problems we will discuss today will be specific to our industry, our semiconductor process, and where AI might be even more may have even more challenges than in the other spaces, right? So as we all know, we are walking towards this future where we're going to have a lot of AI, we're going to be using a lot of it, and a lot of it is going to be used potentially to generate various parts of our design, whether it is analog design or RTL or whatever. But there are some unique challenges that we believe will hold back the true potential of generative AI in our space, and these problems should be addressed and should be addressed upfront in order to make sure that we don't run into these blockers that will stop us from truly using the potential of Gen AI in our space. And uniquely to semiconductors, uniquely to the hardware design industry, are these four things that we have identified. For example, we have a much bigger sensitivity to liability issues, to data provenance issues in the semiconductor space compared to other spaces. There's a whole lot of traceability that we need to build into our systems in order to really make sure that we don't run into problems there. There's also a very, very expensive process, so if you do make mistakes, those mistakes are really hard to correct. The further you go with generated code, the more expensive it gets to recover from these mistakes. And finally, we're talking about the data quality concerns. Almost everybody who's worked in semiconductors knows that every single company, every single team has its own set of standards, has its own way of writing and developing their designs. And we want to make sure that those quality standards and those particular things that you as a team have developed over years and decades of work are retained and managed well with the generative AI tools that generate code for you, right? So these tend to be fairly unique to our industry because, as I said, this situation tends to be a lot more prevalent in our semiconductor space compared to other spaces. So in order to specifically address this, we want to have a clear and auditable data provenance for all training data sets. So now, when you look at any particular workflow where you're trying to generate code, let's say, maybe not right away, maybe a couple of years in the future, whenever you get to the point where you start to trust or start to use these models more and more, you need to make sure that there are two kinds of problems that you're looking at. One is, what is the kind of data that was used to train your models? And then the other part is, was that generated code actually doing what you wanted to do? Was it effective? Was the training good enough, right? So the second part we will not address today because that is more about the kind of model you're using, the kind of LLMs that you're using, or how those LLMs have been parameterized and trained, right? Well, we're talking about the first part of the problem, which is what was used to actually train that model. And that is specifically a problem of building the data sets and making sure that those data sets are traceable. So you need clear and auditable data provenance for all of your training data sets. Where did every single piece of data come from, and what was its role in your training data set? The second thing is the traceability of all the various blocks, right? It's not just an undifferentiated blob of data that you're training your data set on. You want to be able to differentiate that into functional blocks that then allow you to say that this is the function of this block, or how do you describe a particular block that you're using for training. And then the third, and actually I think one of the most significant problems is, do you have the rights to train that, rights to the data that you're actually training your blocks on? Now, this is a very thorny problem because quite often, as we all know, when we build out our chips, we tend to use, or we tend to purchase external IP. We tend to build, these designs with IPs that, or content that is not necessarily completely owned by us. There's royalty issues, there's proprietary liability issues. So that is actually a very, very important problem where you can't just take your entire design and feed it into training models and hope for the best, right? And then there is also highly sensitive or highly secure IP that you're not supposed to be training your data sets on. For example, you might have export controls on certain IPs. You might have technologies that are not allowed to leave a certain geographical boundary, right? So all of these things lead you to a situation where you have to be very careful about what is being used to train your AI data sets. So when we talk about all of these problems, we believe that one way to solve these problems is to have a strong IP lifecycle management built into your workflow. Now, the term IP lifecycle management is maybe a little narrow in the way I'm talking about it, but really, when we talk about IP lifecycle management and we talk about IPs in general, we talk about any design block that you use as part of your design, right? Now, these blocks could be designs that you have built yourself, built in a previous project, purchased from external vendors, et cetera. So if you treat every single design block that you have as an IP, then you can attach a life cycle to those blocks, you can attach traceability to those blocks, and that, when you feed that into training data sets, you get a lot more control of what's going in, and therefore you have a lot higher confidence in what that training data set was leading you to, right? So effectively, you're talking about taking a large design and always breaking it down to a set of IPs, and then attaching life cycles to those IPs. Then with each IP comes its provenance. Where did this IP come from? It's not just a part of a design that you don't really know about or care about. You know that this particular block was designed by this team of engineers at this point in time, and these are the variations of these blocks that are available to you. And then you can make a decision whether a particular block can contribute to a training data set or not, because you have provenance of every single block in your design. You can also add rules. There are some IPs, some secure IPs or external IPs or blocks that are maybe within your particular design environment, but should never be used for training because of various reasons, because of liability reasons, because of export controls, or because of other trust issues that you want to establish, right? So you can put in rules that say that certain data sets shall never be used for training, for example. The other thing is incremental training, right? So obviously, as you go through your design blocks and you enhance them, you fix bugs, you add more features, et cetera, these incremental blocks can now then add to your further training corpus, but you need to make sure that you're tracking the evolution of these blocks so that you can feed more and more accurate and well-designed data into your training data sets. Now, having done all that, you can now start building a workflow that allows you to innovate and more efficiently with the data sets that you have in mind, because you know the provenance of all the data, you know how the data is evolving, and what new data needs to get in there because things are changing rapidly in the design environment around you. So how this works is, like I said, you take a design, break it down into a bunch of dependent hierarchical IPs. These dependent hierarchical IPs can be anything. It can be, like I said, blocks that you've purchased from other external vendors. It can be blocks that you've designed yourself, blocks that you're coming from a previous design, or maybe from central IP teams. All of the stuff that you are contributing into your design, you break it down into IPs, and you attach life cycles around it, right? Now, in addition to the IPs themselves, there's a ton of information that goes with that particular design. You're talking about technical specs, you're talking about workflows driven through tools. For example, we have at Perforce, we had a collaboration announcement this DAC with Siemens. And Siemens has IP validation tools, IP quality assurance tools, cross-check and all of those tools that they provide, which generate metadata on top of your design. That metadata should be attached now to the IP version on which that workflow was run. So when you're training a model, you have not just the design data, but the context and the metadata on which allows the model to get more intelligence about what's going on, right? So taking data, which is your design, attaching the metadata to it on the specific version of that data that was used to generate that metadata is very important when you want to train these models, right? So it's data, design files, and all the other associated metadata along with it, which might include technical specs, workflow output, dependencies, the hierarchy, and so on, as well as you could geofence certain IPs. You could say that certain IPs are very sensitive and should never leave a particular fenced area within your network, or should never be used for training, for example, right? So all of this is metadata that describes the IP better, which allows you to build rules around what data sets can be created for your training models. So this shows an example of, a very, very, how shall I say, simplified example of what a training data set might look like or a training workflow might look like. And you're talking about having the raw data, which is essentially design files and attached metadata, et cetera. It could be in CSV formats. It could be in other data lake formats that you can support, which is fed into pre-processing, training, validation, and testing. So you take data, you split it into various pieces after having cleaned it up, made sure it is available for the right sources. And once you have that data, you split it into training models. All of this needs to be completely traceable. And the point of this slide is to show that the data moves through your pipeline in a traceable way, so you know that when you have established what that training data set is, you can look back through the pipeline and see where it came from. What was the exact content? And now this data, by the way, is not static. You would make this pipeline, you would run it once or twice or a number of times until you achieve the result you want out of your model. However, you might want to run it over and over again because the data itself is evolving, right? So having traceability both in the workflow as well as over time is critically important to make sure that this data, that is basically the underlying platform on which you're building all of this training, is always accurate and does not lead you to pollute that data with IPs that are not supposed to be there. So this kind of shows a implementation that we just did to kind of get around this problem of data leakage into this model. And we're talking about all the resources, including the models themselves, being modeled as IPs in the system. That's one way to do it. I mean, you could have other ways of doing it. But then it shows how even a very simple training workflow can get rapidly pretty complex. And believe me, this is a very simple training model. It was just an exercise that we did to put together a simple training model. And the complexity was already obvious. When you have a real life example or real life project where you're actually building all of this, the complexity is going to be 10x this, which means that you need to build the appropriate controls in place, because it's very easy for data to leak into it. For example, if you have data from a previous design that you purchased from a vendor, you could, if your model is trained and you just ask the model, hey, give me another version of that model that you used, a block that you used previously, the model may be able to spit out that. But now you've violated a bunch of rules. You've trained it on data that you're not supposed to train it on, and you do not know that you did it, and you're exposing yourself to all kinds of liability. So the value of putting together this guardrails or these pipelines within your system is obvious, right? You easily manage data, which is a key problem. Not only the fact that you have a lot of it, it is changing all the time, and it is very prone to leakage, which means you could be including data in there which you're not supposed to. So you can easily manage data because everything is modularized into IPs. IPs have their life cycle, IPs have their history, and before you can build any training data set, you build it through this IP data management platform, which allows you to include and exclude, and build rules around each of these IPs, which allows you to easily include and exclude IPs from training data sets. And of course, you can use the data management tool that best suits you, I mean, there are plenty available. You could just use a data, you could use a SQL database, for example, if it's really large. You could use Perforce. You could use Git. You could use whatever you choose. But you have to use some kind of data management so that you're not just pointing to some location in a file somewhere and hoping for the best, right? So use data management, and then you build workspaces by asking for the data and not by ad hoc copying data around, right? So every time you want to build a training run, you ask a system, give me the data from the repository that is managed, and then you build that workspace out, and then finally, you get a fully traceable ecosystem because you're not training on arbitrary data. You're training on data that has been delivered to you through a system that knows what's going on with that data. And finally, metadata, right? That's another key and important piece of what you're using the training data sets for. It's not just the design, but what did that design actually achieve? What was the parameters that were used to create that design? What was the verification results on that design, regression runs maybe, and bugs that were associated with, right? All the stuff that informs your model beyond the data itself is now available within your context because you have asked the system to deliver the data and metadata to you in a single package. And finally, you can do model lineage as well. So you can say, I'm using an LLM today. There are a variety of LLMs available. Somebody mentioned that there's a new LLM created every 4 minutes somewhere in the world. So yes, there's a few of them out there. You could be choosing, whichever LLM version, and that's changing rapidly as well. And you have a variety of choices to make here. So you could also model the LLM itself in the same system as an IP so that you know, as part of your workflow, which version of which LLM was used to train at any given particular time. So that's the scope of what I wanted to discuss. Anybody, any questions? I'm happy to take questions. All right, thank you.